Hi everyone. In this lesson we're going to be proving that a quadrilateral is a parallelogram. This is part 2 of the lesson, in which we're actually going to be doing proofs to show that a quadrilateral is a parallelogram. So here are the 5 theorems from the last lesson. The first one requires both pairs of opposite sides to be parallel in order for the quadrilateral to be a parallelogram. The number 2 requires both pairs of opposite sides congruent in order to be a parallelogram. Number 3 requires one pair of opposite sides that is both congruent and parallel. Number 4 requires both pairs of opposite angles congruent. And number 5 requires diagonals bisecting each other. So today I'm going to give one example with number 1 and one example with number 3. Number 3 is usually and probably the most used because it could be the shortest way to prove that you have a parallelogram. And so I'm going to do one example with number 3. And I hope you can get the idea from these 2 examples on how to do proofs using the other methods that I'm not doing today. So let's look at number 1. Of course, the instructions say, write a clear and organized 2-column proof, mark the diagram. In number 1, we have quadrilateral ABCD that's given, with angle 1 congruent to angle 4 and angle 2 congruent to angle 3. That's all given. And you have to prove that ABCD is a parallelogram. So if you have these givens, the first thing that we're going to do is mark them. So what we know is that angle 1 is congruent to angle 4 and angle 3 is congruent to angle 2. So what can we get from this? Well, if we look at the diagram, angle 1 and angle 4, these angles are forming the Z with segments BC and AD. So what we have here is alternating triangles that are congruent, and that would make BC parallel to AD. So here we are using the converse of the alternating triangles theorem, which would say if you have 2 lines intersected by a transversal and the alternating triangles are congruent, then those lines are parallel. So that's what it would say. So because angle 1 and angle 4 are congruent, BC and AD are parallel to each other. And now we have that angle 2 and angle 3 are congruent, and we will have to do the same thing that we did with angle 1 and angle 4. If we notice angle 2 and angle 3, they form a Z, but this time they are forming the Z with AV and CD. So for the same reason, AV would be parallel to CD because you have 2 alternating triangles that are congruent, and so we can conclude that these 2 segments would be parallel. So AV is parallel to CD. And now look at what we have. We have both pairs of opposite sides being parallel, and that is theorem number 1 from our table above, which says If both pairs of opposite sides are parallel, then the quadrilateral is a parallelogram. So by the first theorem, we can now conclude that this figure ABCD is a parallelogram. So I have the proof partially done, and so I'm just going to complete it. Statement number 1 says quadrilateral ABCD, that's given. Statement number 2, angle 1 is congruent to angle 4 and angle 2 is congruent to angle 3, that's given. And now we're going to put what we got from the fact that angle 1 is congruent to angle 4 and what we got from the fact that angle 2 is congruent to angle 3. So we got that because angle 1 is congruent to angle 4, BC is parallel to AD. And because angle 2 is congruent to angle 3, we got that AB is parallel to CD. And the reason would be the converse of the alternate interior angles theorem, which says that, I'm just going to write it in a short way, if alternate interior angles are congruent, then the lines are parallel. And finally, since we have both pairs of opposite sides are parallel, in number 4 we will conclude that ABCD is a parallelogram. So ABCD is a parallelogram. And the reason is the theorem number 1 on the table, which says that if both pairs of opposite sides are parallel, then the quadrilateral is a parallelogram. If both pairs of opposite sides are parallel, then it is a parallelogram. Okay, so that's number 1, and now we go to number 2, and it says given rectangle PQRS and QT congruent to SM. We have to prove that TRMP is a parallelogram. So PQRS is a rectangle. And then we have that QT, which is this part here, is congruent to SM, which is this part here. So this piece is congruent to this piece. And then we have to prove that DRMP is a parallelogram. So we want to show that this figure, which I just put it in green, that one is a parallelogram. That is our objective, and we have a rectangle and this piece here congruent to this piece here. So for this one, I'm going to use theorem number 3 on the table, which says that if one pair of opposite sides is both congruent and parallel, then the quadrilateral is a parallelogram. So I'm just going to be working with one pair of sides, one pair of opposite sides, congruent and parallel at the same time. So since I have this information here, QT congruent to SM, I can actually prove that this little piece here, PM, is congruent to CR. Why can I do that? I can do that because we know it is a rectangle, and in a rectangle, opposite sides are congruent, so that would make PR congruent to PS. So those pieces are equal. And since these little pieces here are equal, if we subtract QR minus QT, we will get DR. And if we subtract PS minus SM, we will get PM. And those results would be congruent. And that's how we are going to get one pair of opposite sides that are congruent. Is going to be because this piece is going to be congruent to this one, by using the subtraction property. And now we have to show that this pair, the same pair of opposite sides, are parallel. We already showed that they are congruent. We just need to show that they are parallel. And they will simply be parallel because they are part of the sides of the rectangle, which we know are parallel because a rectangle is also a parallelogram. So the big figure is a parallelogram, but for the small one, we only have these pieces here. So because TR is part of QR, that would be parallel to PM, which is part of PS. Since QR and PS are parallel to each other, because it is a rectangle and a rectangle is a parallelogram. So that's how we are going to get that DR is parallel to PM, and so we have one pair of opposite sides that is both parallel and congruent, which would allow us to conclude that TRMP is a parallelogram. So now I'm going to complete the proof. I have rectangle PQRS given. I'm not going to put anything else in the first statement, because now I'm going to set up what I need in order to do the subtraction to get TR congruent to PM. And so I have to say what is it that I'm going to subtract. I'm going to subtract QR minus TR minus QT, sorry, in order to get TR. So I need to put all that. So QR, and from this one, we're going to subtract QT. And after we do the subtraction, we're going to get as the result TR. But of course, we need something else here. These are all incomplete statements right now. So what we have to say over here, QR is congruent to PS, what's highlighted in yellow. So QR is congruent to PS. Why are they congruent? Because opposite sides of a rectangle are congruent. And now, of course, I need to complete this statement. What is it that I'm going to subtract to PS? I'm going to subtract MS or SM. So here would be QT congruent to SM, which is the statement that I have here. QT congruent to SM. So the reason for number 3 is given. Now after I do the subtraction, of course, QR minus QT is DR and PS minus SM is PM. So these two pieces should also be congruent. And what did we do in order to get this result? We subtracted here. So we got as number 4 the subtraction property. And so I have now this pair of opposite sides that is congruent. I just need to show that we have the same pair of opposite sides parallel, and then we will be done. I'm just going to do that by saying TR is parallel to PM, and the reason is going to be opposite sides of a rectangle are parallel. And since these pieces are part of those sides, these pieces would be parallel to each other. And so now I have the same pair of opposite sides being both congruent and parallel at the same time. And so I can now conclude that TRMP is a parallelogram. And the reason would be our theorem number 3 from the table, which says if one pair of opposite sides is both congruent and parallel, then the quadrilateral is a parallelogram. Just moving up in order to be able to write it. If one pair of opposite sides is both congruent and parallel, then the figure is a parallelogram. Okay, so this would be the end of this proof. And as I said at the beginning, this method is usually the one that is mostly used because it gives us a shorter way. The other ones would be much larger. So I'm giving you an example of how to do this. and just practice with the other ones. I know I haven't given you examples with the other ones. I hope you can get the idea just by using this one. And that will be it for today on how to prove that a quadrilateral is a parallelogram. As always, check the website to see what is the homework.